SwayamPrabha. Digital India. Educated India.
In this lecture, we'll see how we can find the transfer function of a coupled system and also how we can design the closed loop control system. We'll discuss in detail. So first, let me discuss the problem. Consider the linearized pitch dynamics of an aircraft at a steady state or steady level flight. Delta alpha dot equal to minus 0.313 delta alpha plus 56.7 Q plus 0.23 to delta E and Q dot minus 0.0139 delta alpha minus 0.426 Q. In place of Q also you can write delta Q, but here we are writing Q only, plus 0.0203 delta del E and del theta dot equal to 56.7 Q. And where Q is the pitch rate, delta alpha deviation of angle of attack from trim angle of attack and del theta deviation of pitch angle from trim pitch angle. Let's denote the alpha naught and this is theta naught, for example, trim values, and delta daily elevator deflection is basically control. And also we are assuming there is a servo system, elevator servo system, which gives the desired delta E to the system. The elevator servo dynamics given by del delta E dot equal to minus 10 delta E plus 10 voltage. So here V is the input voltage to the elevator servo, and here V is the control voltage to the system, to the servo system. And if you see the closed loop block diagram for this particular system, we can have the closed loop block diagram. So we have to design PID controller. We'll go step by step how we can design the PID controller for this. This is PID control. The output of the PID controller is generated by V, which is going to the servo system here, which is delta del S divided by V of S, and which gives the control, elevator control delta del S to the plant, which is denoted by del theta of S divided by delta S, and the output is del theta. And we are having summing point here where we have desired value of delta theta reference, which is assumed to be 0 for this particular problem. We have to maintain. And here the feedback, this is the feedback, this is negative feedback, this is positive. So this is the closed loop block diagram for this particular problem. And the questions from this problem, first question is, find out the transfer functions g of s equal to del theta of s del delta es, which is basically the plant transfer function, and also you have to find h of s, which is delta del es and v s. So this is the another transfer function which represents this block, and this part represents this block. And second question, we are having sketch. So we'll design the PID control for this problem using the root locus and Ziegler-Nichols method. Sketch the root locus plot for the system with OLTF G of S, H of S. So how to find OLTF? We know OLTF basically, if we consider this is E of S, the total loop gain from starting to this to till this part, the total loop gain of the system in the entire loop, total loop gain. So here we have two transfer function, one GS and HS. PID we have not taken the transfer function here. So here, for designing the root locus, we'll consider one gain at a time. So if it is K is the gain of the PID control, so we will multiply K also here. So that part we will discuss later. So for the time being, for this is the two transfer function we are having, and this is the OLTF. And third question we are having, design a PID controller for the above system, using Ziegler-Nichols method. So this is the problem for us. Now we'll go step by step how we can solve this problem. So here, if you notice, we have to find the transfer function del theta with respect to del es. But if you look our dynamics model, this is coupled actually. So we have to use the brute force method or the Cramer's rule what we have discussed in the previous lecture. We can apply those methods and we can find this transfer function. So here we are having, let me define this equation number 1, the whole equation. And here I'm not writing the dynamics part again, directly applying the Laplace transform to those equations. Applying Laplace transform to equation 1 by assuming zero initial conditions for each state variable, yield. So we can write for the first equation, we can write S plus 0.313 delta alpha is minus 56.7 Q is equal to 0.232 delta ES. For the second equation, we can write S plus 0.426 QS plus 0.0139 delta alpha is equal to 0.0203 delta ds. And for the third equation, we can write S delta theta is equal to 0 here should be, and minus 56.7 U of S. So this is the equations which are written in Laplace domain. Now, if you write in matrix for all this equation, writing in matrix form, we can write S plus 0.313 minus 56.70 0.0139 S plus 0.426 and 0, and the third row will be 0 minus 56.7, then it will come S into delta alpha S QS and delta theta S. And here we'll have 0.232 0.0203 and 0, and we'll have delta ds. Now, if we divide both sides by delta ds, then we will have S plus 0.313 minus 56.70 0.0139 S plus 0.426 56.7 basis, and thus for this vector we'll have delta alpha S divided by delta ds, del QS divided by delta ds, and delta theta S divided by delta ds. and it will have 0.232, 0.02030. And from this equation, we can write, I'm directly writing the expression. So steps you can follow what you have done before. So from this equation, delta theta of S and delta daily S, we can obtain 1.151 S plus 0.1774 divided by S cube plus 0.739 S square plus 0.9215 S. So this is the transfer function for the plant transfer function we found. This is the plant transfer function. For this we have found, which relates between the delta theta and delta del S. So here this is the plant transfer function. Now we have to find the HS. So let's take the another equation, which is the servo, which relates the servo system, and delta E shows that equation, the elevator dynamics, we can write delta del E dot equal to minus 10 delta del E plus 10V. And if you apply the Laplace transform with zero initial condition, we can find H of S equal to delta del S divided by PS, which is equal to 10 by S plus 10. So this is the HS. We'll find the second. So first problem is done. So now we'll do the second part. So here OLTF, we can consider GS HS, which is 10 into 1.151 S plus 0.1774. Okay, I'm assuming in the control we are having K, the gain K. In the control initially we are using some K, and which we'll find from the root locus. So here K into this, and this is also K, we are writing, divided by S into S plus 10, S square plus 0.739 S square. S we take common outside, so it is S only, and plus 0.9215. So here also we can, because the control we have considered here, that's K, so we can write K also here. From this OLTF, we'll find the zeros. The zeros we have minus G1, only one zero is there. So minus 0.1774 divided by 1.151, which is minus 0.1541. In the poles, we are having P1 equal to 0, P2 we are having minus 10, and P3 and 4 we can write minus 0.739 plus minus root over 0.739 square minus 4 into 0.9215 and divide by 2. So it comes out to be minus 0.3695 plus minus 0.8860 I. So we have complex conjugate root. Now here, if you notice here, number of 4, n equal to 4 and m equal to 1, number of zeros, and n minus m equal to 3. So now let's find the angle of asymptotes. Angle of asymptote, we can find 180 degree plus into 1 divided by 3, which is 60 degree. So there are n minus m equal to 3, so 3 angle will be there, 3 asymptotes. 180 degree into 3 divided by 3, which is 180 degree, and 180 degree into 5 divided by 3, which is 300 degree, which is nothing but 60 degree, minus 60 degree. And centroid we are having, let's find the centroid. First, let's find all the parameters which will help us to draw the root locus. Centroid, this is asymptotes. So centroid we can find minus 10 plus minus 0.3695 plus 0.860 I minus 0.3695 minus 0.860 minus 8860, so that is also 8860. This is I, and plus 0.1541 whole divided by 3, and the value comes out to be minus 10.5849 divided by 3 is 3.5283. So this is the centroid for the root locus. Now we have to find okay, P0, P1 equal to 0, P2 equal to minus 10, and G1 equal to minus 0.1541 lie on the real axis as one angle of asymptote is 180 degree. So there will be one branch will go, there will be one branch asymptotes branch will go from P2 equal to 0 to infinity. It's quite obvious. And another branch will go from P1 equal to 0 to C1 equal to minus 0.1541. So this is what will happen in the real axis. Now there are two complex conjugate poles which are on the left hand side. So there will be angle of departure from P3 and P4. So first let's find the angle of departure from the P3. Angle of departure from P3 is 180 degree plus P3 minus G1 minus P3 minus P1 minus P3 minus P2. This is how we find the angle of departure, P3 minus P4. And these values are 180 degree plus minus 0.2154 plus 0.8860 I and minus 0.3965 plus 0.8860 I and minus 9.6305 plus 0.8860 I and minus 90 degree. For this, we can find 90 degree plus 180 degree minus tan inverse. So this is the condition for, we can apply the tan inverse. So here tan inverse 0.88, the imaginary part divided by real part, 2154 minus 180 degree tan inverse 0.8860 divided by 0.3695 and minus tan inverse 0.8860 divided by 9.6305. And after calculating all these terms, we are getting 90 degree minus 76.3356 degree plus 63.3618 degree and minus 5.2564 degree and finally 75.77, right, 764 degree. So this is the value we are getting for the angle of departure. So as the root locus is symmetric from the real axis, another angle of departure in the imaginary axis as well. Let me write, as the root locus is symmetric with respect to real axis, angle of departure from P4 will be minus 75.7648 degree. This, okay, 3 digits, 7 So now we have to find another term, intersection with the imaginary axis. So angle of departure we have found, and intersection with imaginary axis. So for this, we have to find the closed loop characteristic equation. The same process what we have done before. Closed loop characteristic equation yields to be S into S plus 10 S squared plus 0.739 S and plus 0.9215 plus K10 1.151 is plus 0.1774 equal to 0. And from this, if you substitute, so now we have to find that intersection with the imaginary axis. For intersection with j omega axis, is equal to j omega, we substitute in the above equation. And finally, after, I'm just leaving some step for you. So finally, we'll have the expression omega to the 4 minus 10.74 I omega q 8.311 omega square plus 9.215 plus 4.51 k j omega plus 1.774 into k equal to 0. And we can, in this part we'll have two parts, one imaginary part and real part. So we can write, we can divide omega to the 4 minus 8.311 omega square, and another real part is this one, plus 1.774 into k. And the imaginary part, 10.74 omega q minus 9.215 plus 11.51 k into omega equal to 0. And from this we'll have omega square equal to 8.311 plus minus 8.311 square minus 4 into 1.774 into k divided by 2. And from this we'll get omega equal to 0 and omega equal to, we get plus minus 9.215 plus 11.51 k and divided by 10.74. So here we can find omega equal to 0 and k equal to 0 is satisfied, or you can say is a solution. Again, we can write 8.311 plus minus root over 8.311 square minus 4.1.774 k divided by 2, or we can write equal to 9.215 and plus 11.51 k divided by 10.74. So here we can write this expression, and after simplifying this expression we are getting 1.1485 k square minus 5.2939 k minus 6.3947 equal to 0. And from this equation we can find k. So from this k we can find 5.6031 and minus 0.9 9937. It is clear that as k greater than 0, so we can write if it is k equal to 5.6031, and for this case omega will be plus minus 9.215 plus 11.51k divided by 10.74, and from this plus minus we can write 2.6197. So we can say, so this is the value we have to take for k. This is not satisfying because the k, if you see the angle condition, this will not satisfy, and the center of CG and the centered concept, and from this it is not clear. So here we can write, so the root locus intersects the imaginary axis at plus minus 2.6197 I, this point. This is the point versus the j omega axis. This is the value we are going to consider for k, this value. So this value we are going to consider. So here we can say k ultimate. So here k ultimate, which you can write ku equal to 5.6031, and at that ku the omega is 2.619. This k value you can find from the another approach what we have done in the first half of the course, which is basically the Raoult-Harris stability criteria. Through that table, Raoult table, we can also find this ultimate gain k. From the characteristic equation, we can find the Raoult table and we can find the value. And now, if you are having this frequency, you can also find the time period tu, ultimate 2 pi divided by omega, which is 2 pi divided by 2.6197, which is 2.3984. And so we are having all the values, k we are having, tu we are having. So using these two parameters, we can find the PID gains using Nicholas rule. So we can find Kp, let's find the proportional gain, which is 0.6 Kpu, and 0.6 into 5.6031. So this is the value comes to 3.3619, and integral gain 0.6 Ku divided by 0.5 Tu, which is 2.8034, and Kd you can write 0.6 Ku into 0.125 Tu, which is 3.3619 into 0.125 into 2.3984, which is 1.0079. So this is the gains for the PID control. So now we can structure the PID controller, which is PID control. This is basically, we can write 3.3619 plus 2.8034 divided by S, and 1.0079 into S. So this is the PID control structure which can be incorporated in our control block diagram, and from this we can come up with a system which is going to be stable, because this is the gain we have found through the Ziegler's Nichols rule. So let's stop it here. Have another lecture in this course where I'll give the brief of the course, how it was conducted, and what are the contents being delivered. I'll give the brief conclusion of this course. Then we'll wind up this course. Thank you very much.